All right, we did it. We've made it to the last portion of our conversation about Chapter 2, Section 4, the precise definition of a limit. And the last thing I wanted to do with you is to take a look at some more example problems, which I'll be pulling from a homework assignment that I created in WebAssign, which is a wonderful McGraw-Hill product, in case you're investigating the possibility of making a switch as an educator out there, or if you're a student who's fed up with your current learning management system, maybe encourage your professor to check out WebAssign. It's a nice piece of software. Right, anyway, by the way, I'm not sponsored by WebAssign or McGraw-Hill. I just like it. So I'm going to go through this homework assignment. I created a PDF, just printed my homework assignment to a PDF, and thought we'd go through and look at some solutions. If you've watched the two previous sections or section videos here from 2.4, a lot of this stuff is going to be a breeze. You recognize this kind of a diagram. Maybe let's try green and see how it shows. That's pretty good. You're seeing the number 1 here. This is your capital. That's a 4. Now it's a capital L. That's your capital L value, which is your limit. The difference between 1 and 1.2 and 1 and 0.8, that's a difference of 0.2. So this is certainly your epsilon value, which is 0.2. And we work with those two resulting values, those two resulting y values from having added and subtracted epsilon, and we take those y values and we map them over to their corresponding points on our curve. We drop down, we see what the resulting x value is. Then we do the same thing with our other y value. We map it over, we hit the curve at this point, we drop it down, we find the resulting x value. And then we look for the difference between. Now this number 1 I didn't mention, but that's our lowercase a from our limit statement. The limit as x approaches a of whatever the function happens to be. In this case it is f of x is equal to capital L. So I had addressed everything except for the lowercase a. The lowercase a is this 1 right here. So I'm looking at the difference between that a value of 1 and this resulting x value of 1.1. And then the difference between my a value of 1 and the other resulting x value of 0.7. You'll calculate what those two distances are horizontally. That's a 0.1 and a 0.3. Don't think about it as a negative 0.3. We're not concerned with direction here. We're just concerned with distance. So we're using absolute values. So you've got 0.1 and 0.3. Which of those two values are you going to assign to delta? Always the lesser of the two. Problem number 2, same idea, just a different graph. Still looking for delta. Problem number 3, we're being told that a graphing calculator is recommended, and that's because the majority of us, well, a bunch of us might know what the graph of the tangent of x looks like, but when you take tan x and you shift it to the right 1 unit. Now tangent, remember, has a period of pi, and it has asymptotes at negative pi over 2 and positive pi over 2. And now we're going to slide it to the right 1 unit. I'm not really super excited about graphing that anymore. So a graphing utility might be nice. Remember that, oh, you know what? I just said sliding it to the right 1 unit. That's a force of habit. I teach enough algebra classes that I'm looking at this like it's a horizontal shift problem or a vertical shift problem. Let's just pause and slow our roll here for a second and identify the different components of what's going on here. This is obviously delta, which we don't know what it is yet. This is our a value that our limit is, our x values are approaching in the limit statement. These are, of course, our x values, and tan of x is our function, and 1 is our limit. And when I say tan of x is our function, I also mean that these are our y values. We're taking x values that are near pi over 4 We're plugging them into the tangent function and generating y values. And we want those y values to be within 0.2 of our limit, which is 1. So if I were you, I would indeed use a graphing calculator if you have one, or use desmos.com as a free graphing utility and draw yourself the graph. Our tangent function looks something like this in between our vertical asymptotes, which are at negative pi over 2 and pi over 2. The a value that we're approaching is pi over 4, which is right here. The desired limit value is 1, which does correspond to the tangent of pi over 4. So that's a 1, and there's your pi over 4. And we want our y values to stay within plus or minus 0.2. So we go up to 1.2, and we'll come down to positive 0.8. And those are the points from which you would want to draw some horizontal lines over and hit your function and find the corresponding x values. Freehand, I had to make this line a little bit angled, otherwise it was going to land on pi over 4, which would not be correct. You're going to need these x values, and then you're going to need to check these distances from pi over 4 to one x value, from pi over 4 to the other x value, and choose the lesser of those two values, or distances, or differences, to be your delta value. Maybe I'll make a video about how to use Desmos, and then a separate video about how to use the TI grapher, although I'm sure those videos already exist. We'll see what I have time for. Graphing calculators recommended. This is the exact same process, except we're being given two different epsilon values instead of only one epsilon value. In the previous problem, the epsilon value was given to us kind of low-key by putting it at the end of this inequality statement. Okay, that's how we found out what epsilon was. And our a value was here inside of these absolute value bars, and our function was tucked inside of these absolute values, as was our limit. Okay, look at this problem number 3. There's no actual limit statement. This is just one way of phrasing a limit statement. Okay? In the next problem, in number 4, we're legitimately being presented very directly with a limit statement. The lowercase a value is very obvious. The function is very obvious. Capital L is very obvious. Epsilon's being handed to us on a silver platter. And then you have to go forth and find a couple of delta values, but you can find them by using the same process that we just used in the previous problem. It's extracting the data that's being presented to you in a different way that's maybe the challenging part about this problem. This problem is still very similar, and at the same time it's different. It's different because this is a limit going to infinity. We're working with tangent squared as x approaches pi over 2. Remember that the tangent graph, which I drew just a couple of slides earlier, looks like this. And tangent squared would take the y value of every point on this graph, including at the origin and in the first quadrant. Imagine taking all of those points, keeping their x values the same, but squaring their y values. And if you squared their y values, you're going to get some interesting results. For example, negative 1/2, if our y value right here is negative 1/2 and you square that, you get a positive, because it's a negative times a negative, 1/2 times negative 1/2. So you get a positive, but it becomes a quarter, which is interesting. So it would actually be above the x-axis, but closer to it. And that's going to happen until you hit 1, or negative 1. So if this point right here has an x-coordinate of negative 1, You square that, you're going to get positive 1, it's going to move up to here. And at negative 2 is going to become positive 4. So this thing is going to climb. It's going to stay low for longer, but then it's going to climb really fast. And it will be symmetric about the y-axis. It's going to climb equally as fast over there in the first quadrant. So it's going to look sort of like a parabola trapped in between two asymptotes. It's going to be getting vertical really fast. So now you've got that graph. My pen is giving me a hard time. Climbing really fast, symmetric about the y-axis, also climbing really fast. And we want to know what are the delta values that are going to constrain us as we approach I have to make my graph a little bit more complete because we're sliding all the way over here to pi over 2. Our x values are approaching pi over 2. We want our y values to get large. We want them to be over 100. So where do I need to be on either side of pi over 2 so that my y values stay above 100? So if I had drawn this a little bit better, considerably better, this should also be symmetric around or about pi over 2. So we need to know these x values so that we can figure out what this distance is, so that we can determine our delta value. It would be you could do this with a scientific calculator. Is that true? Could you really do it with a scientific calculator? I bet you could do this with a scientific calculator. I love a good challenge. Yeah, you just have to set tan squared of x equal to 100 and solve for x. Take the square root of both sides, take the inverse tan of both sides. Make sure you're in radian mode. You're going to get a nasty looking radian value, and then you've got to find the difference between that and pi over 2. Piece of cake. That's your delta value. I'm going to let you rewind that and listen to that like 6 or 8 times, whatever it takes, until you can figure out what I said, and then go and do it. And then redo the process with 1,000. And then if you still want to go in and try it with a graphing calculator or Desmos, be my guest. But for those of you who don't have a grapher, I say you can do it with a scientific calculator, which means you can do it with your phone. But don't use your phone on an exam. So better that you practice with an actual calculator. This is problem number 6. There's a machinist being required to make a circular metal disc. There's a radius value that's producing the disc. We're talking about area of the disc. Don't forget that the area of a disc is equal to pi r squared. Don't forget to round to 4 decimal places. You've got an error tolerance of plus or minus 5 centimeters squared. Centimeters squared constitutes an area. The machinist must control the radius. Alright, so it's sounding like area is being represented by the y values and radius is being represented by x values. And I have read through this problem, and I think that this is a good one for you to read through and explore on your own, because you're going to have to make some determinations about what these different variables represent. And I think that that's going to be nice practice for you after all of the watching of example problems that you've done. To make some of these determinations on your own is going to really help it click. And in addition to extracting an epsilon value from a word problem and then going through the motions that I just described algebraically in order to determine, your delta value. It's going to be fun. It's going to be so rewarding. You're going to love it when it's over. Find the largest number delta such that this is less than this, where epsilon is equal to 0.5. This is a piece of cake. You've done like a trillion of these now. And then we're just repeating it for part B there with a different epsilon value. Oh my gosh, and it's a linear function inside of here. Crazy. Yep, you got that. Tell me there's more. I hope there's more. Prove that the statement using the epsilon delta definition of a limit, I like to say delta epsilon because that's alphabetical order, of this limit, locate lowercase a, locate your function, locate your capital L value, and then notice in the body of the problem it says given epsilon greater than 0. I'm just glancing through this. Yeah, you're not being given a specific epsilon number, so you're going to want to work this one in generality. So this is going to be the first problem of this type that you're working on your own maybe, but thankfully you've got drop downs to give you some options to help guide you. The majority of the thought process is there. We've seen a thought process like this one that starts with but and takes us all the way through to here, and that's where we ended up tinkering with the epsilon statement and making it look kind of like the delta statement, and then matching up the pieces and making our substitution in order to determine our delta value. It's just presented a little bit differently, but all the same content is there, so I want you to do that one. And you know what the graph of the function is, so you should be able to select the correct one of these graphs. Your x value is approaching 5, your limit is 4, which means you're approaching 4, so you've got your 5s and your 4s there. You just need to know what your blue line should look like based on what your function is. I think you can do that, and you might want to do that first before you answer the rest of that question. Do the graphing part first. In number 9, I'd like to make my screen bigger so I don't have to keep looking down. Oh, can't do that. Maybe I can make this one bigger. Nope, that. Well, a little bit bigger. Okay. Prove the statement using epsilon delta definition of a limit. Same process as number 8, just a different function. And this one you've got a denominator approaching 0, so wonder if there's something you could do to the numerator so that you could cancel out the denominator. Hint, hint, wink, wink, nudge, nudge. See what you can do. Number 10, we're being given a function, and all you're being asked to do is evaluate that function for some input values. I think you can handle that. And, oh, I remember this example didn't print exceptionally well, and I'm not sure why, but we're working with that function 1 over x squared again. As our x value is approaching 0, the limit is equal to positive infinity. So again, we're talking about constraining delta values to keep our y values greater than a particular m value. And we went through the motions of solving this in the first video in this chapter section series. So go back and check out chapter 2, section 4, part 1, and there's a discussion about maybe even this exact problem, but I'm going to leave it to you to investigate that. No need for me to teach it twice. And here in number 12, recommended as a graphing calculator, draw the graphs of f and g and f plus g. Yeah, f and g you could probably graph on your own, but adding them together might be nice to see that happen on a graphing calculator. I bet you could figure out which one it is. Solving a linear inequality. This is a throwback question. It's a review question. Just making sure that you remember how to do that. I've never worked with this interface before, and this is just printed to a PDF, so this doesn't even look accurate, but just be careful and make sure that you're graphing the solution set. So if somehow you're going to use these symbols in order to graph it in the correct location on this number line that they've provided you. And the same thing is happening here. This number 13 is pretty straightforward. solving a linear inequality. If you need to go look that up, you should be able to find solving a linear inequality. Number 14 is solving a rational inequality. And that's a little bit different. The process, you should know how to do this. You've been exposed to this before, but generally speaking, set this equal to 0, set this equal to 0, take those two x values, put them on a number line, and then you're going to have to test x values from these three different regions in order to determine which region worth of x values satisfies this entire statement. Once you know which regions satisfy the statement, you will build your solution in interval notation. Remember that interval notation, if I said, for example, 2, 5 on a number line, we would start at the number 2, coming up to the number 5. We would shade everything between 2 and 5. We would not shade 5 because it's got a parenthesis or an open bracket. We would shade at the number 2 because it has a square bracket or a closed bracket. However, we don't use these open and closed circles anymore. We just bring the exact same notation down. So you'd throw a square bracket on the end at the 2, which closes the interval at that end. And at 5, you'd have a parenthesis or open bracket, which leaves the interval open at that end. So make sure you're choosing the correct symbols in order to answer this question, being mindful that you have a strict inequality there. You do not have an or equal to. Or equal to usually means that you're going to be using a square bracket. So my guess is for number 14, you'll be using parentheses everywhere. But you're going to have to make that determination on your own. And this is an absolute value inequality. I probably have a video about this on my channel. You can go and find a video about it somewhere else. Remember that if you multiply or divide either side of an inequality by a negative number, that you need to flip the sign. And your first task in working with an absolute value inequality is to get the absolute value all alone on one side of the inequality first. Once you have isolated the absolute value, then you'll make a determination as to whether you're going to set it up as a compound inequality or if you're going to go the other way and set it up as two inequalities separated by the word or. Those are your two different options for solving an absolute value inequality. I'm so over Chapter 2, Section 4, I can't even begin to tell you. I don't miss 2.4. I miss you, but not 2.4. See you in 2.5.